Hello all, welcome back to my YouTube channel all about VLSI. In this particular video, we are going to discuss some important terminologies which are present in our PCIe protocol. And in our previous session, we have discussed about what do you mean by root complex and where exactly the root complex is placed and what do you mean by north bridge and what do you mean by south bridge. These particular things we have discussed. And also, we have seen that we were having our North Bridge separate from our processor, but as the technology evolved, we are going to basically integrate that particular North Bridge into the processor itself. So that was the things we have seen in our previous session. Now let us try to understand some more important terminologies in our PCIe. So in this particular session, we are going to discuss PCI bus numbering, bus 0 and bus 1. What do you mean by them? And what is bridges and how we are going to have multi-bus topology and how PCI is evolved into PCIe and the PCI architecture we are going to look into, and we are going to look into configuration space, and we are going to BDF addressing, and what do you mean by enumeration, and what is it we are going to discuss right now. First of all, let us try to understand about PCI bus numbering. Okay, so the bus numbering concept was introduced in our PCI, which was extended into PCIe. So basically, in PCI system, every particular a PCI is an organized and hierarchical tree of buses, bridges, and devices. As we have already seen that in our PCI, I am going to have a shared bus where every device is going to have a common shared bus. Right now, this is a typical architecture of a PCI architecture where we are going to have a host bridge, which is nothing but my CPU. Next, I'm going to have a bus 0. This is the actual bus which is connecting my CPU. So this particular bus is termed as bus 0. And I'm going to have something known as bridge in between, which is going to basically connect the another secondary bus to the primary bus. This is nothing but my bridge. So bus 0 is always the root bus and the first bus enumerated in the system, and it is directly attached to the host bridge or the root complex in the PCI. And bus 1, bus 2 are the secondary buses created whenever a bridge connects to the another bus segment. So if I'm going to have a bridge in between two particular buses, then the upper bus is known as bus 0 and the lower bus is known as the secondary bus or bus 1. So this is the typical architecture where you can see we are going to have a CPU over here, and this is nothing but my system bus, which is connected to a PCA bridge. And over here, I'm going to have one more PCA bus over here, and this is being connected to another PCA bridge, and it is being connected to the PCA bus. You can see this is nothing but my bus 0, and this will be considered as bus 1 and bus 2, and so on. So like this, we are going to have numbering for each and every particular bus when they are differentiated with the help of my bus, with the help of my bridge, right? Now, so over here, coming to my bus 0. So bus 0 is a top level PCA bus in every system. It is created by the host bridge. As we have seen over here, this is basically created by the host bridge, and this is nothing but my bus 0. So the chip that connects CPU or memory controller to the PCI hierarchy, it is nothing. It is termed as bus 0. So device 0 on the bus 0 is conventionally the host bridge itself, and devices soldered into the motherboard like our memory controller or a graphics chip usually sit on this particular bus 0. You can see over here memory controller and other controlling devices are going to sit on this particular bus 0. So there is exactly one bus 0 per host bridge or the root complex domain. And coming to another bus, which is nothing but bus 1, which is a secondary bus. So bus 1 comes into existence only when PCI to PCA bridge is discovered on bus 0. So we have discovered a PCI to PCA bridge on particular bus 0. So that we have another particular bus, which is nothing but my bus 1. Now this particular bus 1 has two sides, a primary bus facing bus 0 and a secondary bus, the new bus it is created, example bus number 1. So you can see over here this particular bus is having two sides, one it is facing towards bus 0 and another is itself, that is nothing but my bus number 1. So any device plugged into a slot behind that particular bridge, it might be an add-in card or it may be a downstream PCI device, it is enumerated into bus number 1. and there can be many bus number one like secondary buses in a system. The specific number depends upon enumeration order, not the physical position. So it's not about the physical position like where exactly this particular bus is placed, but it depends upon the software enumeration. So we are going to discuss what do you mean by software enumeration in great detail. So software is going to enumerate like what is the bus number which should be given to this particular buses, right? Now, but whatever the bus which is being connected to my host controller, that will be definitely given as bus zero. But coming to other buses, it will be given not in a specific order, but it depends upon the software enumeration. Now, so yeah, this is what I was talking about. So bridge is going to connect two bus segments. So this particular PCA to PCA bridge is being connecting bus zero, which is nothing but my primary side, and bus one, which is the secondary side. In the diagram also we have seen. So every particular bridge register set stores three key bus numbers. One is primary bus number, that is this one, and secondary bus number, that is this one, and subordinate bus number, which is the highest numbered bus anywhere below it. So what do I mean by this? Let's say suppose if I'm going to have this particular PCA bridge. So this PCA bridge you can see have two buses. This is PCA bus one. Okay, let's say if I'm going to have a PCA bridge like this, from this PCA bridge I'm going to have two buses. Okay, and this is nothing but my bus number zero. So this is bus zero, and this is bus one, and this is bus two. Now you can see this is nothing but my primary bus, which is bus 0, and this is nothing but my bridge, and this is secondary bus, bus number 1, and this is my third bus, bus number 2. So this particular bus number 2 is said to be a subordinate because this is the highest bus number which is found after the bridge. That is what a subordinate means. So that is what it is written over here. Subordinate bus number, it is the highest numbered bus anywhere below the bridge. Okay, so this particular bridge is going to have the information of these three buses. What is the primary bus number? What is the secondary bus number? What is the subordinate bus number? This PCA bridge is going to have this information. Why it is going to have this information? Because it needs to route the packets, right? So whatever the packets, this concept we are going to discuss in our further sessions. So whatever the packets which we are going to get it from the host, that should be routed like your network. Okay, so we this particular bridge is going to have this information so that it can route properly. Now, so these three fields let the system route configuration and memory transactions to the correct downstream segment. Downstream segment in the sense this one. So it should correctly forward it to whatever the buses which are attached to it. So that is the reason we are this particular bridge is going to contain all the bus numbers. So you can see a multi-bus PCI topology over here where we are going to have bus number host bridge, which is connected to a primary host bus, which is termed as bus number 0. Now, this bus 0 is basically connected to two bridges. This is bridge B and this is bridge A, which is further connected to bus number 1 and further bus number 2. So, bridge A is going to have a primary 0 and secondary 1 and a subordinate 1. And bridge B is connected to primary 0 and secondary is 2 and subordinate here it is also equal to 2 because this is the only bus which is present. So, this is also known as secondary and this is also known as subordinate because there is only one particular bus which is connected. So it's also known as a secondary bus as well as a subordinate bus. So bus numbers reflect discovery order during the enumeration. As I've said you in the previous slide also that this particular discovery is very helpful in enumeration and it is not physical slot position. It is not bus numbers are not allocated depending upon the physical slot positions, but this is basically reflected during the enumeration phase of my software. So you can see over here, the host is basically connected to the bus number 0, where bus 0 is connected with this particular high speed devices. And we are going to have a PCA bridge, which is being connected to my bus number 1. So bus number 1 is connected to PCA peripherals or internet or other PCA devices. Now, so why PCI has to evolve? This already we have seen in our previous session that PCI was having shared bus architecture and clock scaling and wide costly wiring and no fine grained QoS. These are all we have seen in our previous sessions also. Now we will try to understand why PCI was using a bridge at all. Why it can simply use a simple bus, right? So why it was using a bus? Why it was using a bridge? Now we are going to use a bridge basically for reducing the electrical load limits. So a single PCI bus can only drive a limited number of device loads. So if the device loads has been increased, we cannot basically drive all the loads using a single bus. That's the reason I'm going to have a bridge in between. So a bridge creates a fresh electrical signals so that more devices can be added. So you can see over here, if I'm going to connect all the devices to this same bus, then this particular bus cannot drive all this particular devices. So that's the reason what I'm going to have. I'm going to have a bridge in between so that this bridge is used to attach more number of devices to the bus. Okay, so this is where I can use a bridge. And one more is fan out. So splitting into multiple bus segments let the system fan out to far more devices than one shared bus concept. That is what we have seen over here. And isolating traffic domains. So grouping devices like SCSI or routers and expansion peripherals onto their own bus keeps the bus arbitration and traffic separate from the host primary segment. So you can see over here we have connected all the peripherals like routers or internet or different kind of LANs and all to a separate particular bus, so the all the traffic which is being present will be local to this bus, that will be not being combined with your original bus, which is nothing but my bus number 0. And I can also plug and play whatever the modules which I need to have with this particular bus number 1, so that I'm not worried about with the original bus. So in the bus number 1 I can basically insert any particular devices, or I can basically remove any particular devices, which will be completely isolated with your host bus. So that is what this we are going to use a particular bridge in our PCI, not in PCIe. We are using it in PCI. Now, coming to PCIe, we are going to have a point to point. We are not going to use a shared bus. So this is the difference between our PCIe and PCI, where in the case of my PCI, I was using a shared bus, whereas in the case of my PCIe, I'm not at all going to use a shared bus. So PCI Express replaces the shared bus parallel bus with a dedicated serial point-to-point links called lanes. I'm going to have something known as lanes, which are bundled into X1, X4, X8, and X16. We are going to discuss what is this particular lanes and what is this numbering and all. And each device is going to get its own private link to a switch or the root complex port, and there is no bus contention. And despite the physical redesign, so here you can see we are going to have a point to point connection from one device to that is my root complex to the actual PCIe compliant device, and I'm not going to this particular devices are not going to share a common bus. Now, what is that we are having? So, due to this, we are going to first of all solve the arbitration problem, and we are going to have high speed links. These are basically high speed links. Now, you can see then there is no need to use a particular bridge at all. But so, despite the physical redesign, PCIe is preserving the PCI software model and configuration space. It is restoring BDF addressing and bus device function enumeration, and all are going forward unchanged. So what do you mean by configuration space? What do you mean by BDF addressing? And all we are going to discuss. And one more thing over here, you can see in PCIe, we are not at all physically using any kind of bridge, but whatever the softwares which we have developed for PCI are logically using this kind of bridge conventions and all, and it is difficult to change it again the conventions and for our PCIe. So what are we going to do in our PCIe is we are not actually going to have any physical bridges present, but we are considering them as logically present, like a virtual. They are not physically present, they are virtually present. So what do I mean by this? Let us try to discuss this in great detail. So first of all, let us see the architecture of my PCIe, where I'm going to have a CPU, which is being connected to a root complex. Root complex, it is going to basically connect with memory interface and PCI to PCI bridge and PCI endpoint using this PCIe lanes. And I'm going to have something known as switch over here. So what is the switch going to do? It is going to connect multiple PCIe endpoints. That is nothing but my actual devices using the PCIe interface. So this switch is going to decide which particular link should be connected to the root complex at a single time. Not all the particular links are connected. So the switch is going to decide which particular link should be connected. Okay. So this is where we are going to use a switch for establishing multiple components work but we are going to have a single point to point connection, but not a shared connection, right? Now, first of all, before going to discuss about what is that logical thing which I was talking about and physically remove the bridge but having logically connected and virtually connected, first of all, let us see the root complex roles and responsibilities. This we have already seen in our previous session also, which is a fabric entry point and it is going to own bus number 0 and it is going to host the root ports and it is going to generate and translate the transactions and start enumeration. Enumeration we are going to see in our upcoming slides, and ecam based we are going to discuss in our upcoming sessions, and send all the responsibilities of my root complex. So basically, enumeration is a process of discovering every device in the PCI hierarchy. So when we are going to do the enumeration, my BIOS or whatever the operating system is going to walk through the entire PCI hierarchy for discovering what is where is the bus and what is the device and what is the function, and it is going to discover everything, right? And this particular combination, so basically, my PCA hierarchy is going to discover which bus, device, and function combinations actually have the hardware present, and it is going to learn about the topology, and it is going to also discover everything. Where is the switch? Where is the endpoints and all? It is going to discover every particular thing. That is nothing but my enumeration. Okay, so enumeration is kind of thing like it is going to discover what and all which is present inside my hierarchy in the PCA hierarchy. So you can see over here, so from the root complex, it is going to bridge and it is going to endpoints and it is going to bridges and endpoints and all. So in the enumeration stage, we are going to discover each and every particular component which is present in our hierarchy. So how it is going to work? We are going to start at bus 0, that means our root complex, and we are going to and the probe device 0, and read the vendor id register, and it is going to return this particular value. That means there is no existence over there. And if the device exists and the bridge header it is type 1, then recursive explore the bus behind it, and it is going to have the depth first search, and it is going to assign each newly discovered bus the next free bus number, and it is going to record in the bridge own bus number registers, and it is going to continue until every particular branch of the tree has fully walked. So this is nothing but my enumeration, and the bus numbers are assigned in order branches are discovered, not by the physical slot position. So this is the process of enumeration where it is going to discover every particular thing. Now, we also need to know what is known as configuration. So, in the case of enumeration, we are going to basically decide three particular things. One is bus number, and another is device, and another is functionality. It is known as BDF: bus number, device, and function. So, these are the different three terminologies my enumeration is going to discover. Next is configuration. So configuration is nothing but programming the discovered devices so that they can be used. Now, once the enumeration has found a particular device, configuration is the step where my host is going to write down the values inside this device configuration. So every particular device is going to have something known as dedicated configuration space, and after enumeration is completed, my operating system is going to write down into that particular space into the configuration registers, so that the device can be active and it can be addressable by the participant on the bus. Okay, so what is going to happen in the configuration? We are going to have the bar sizing and allocation. Bar is nothing but base address register. So we are going to, in this particular step, we are going to determine how much memory input output space and each particular bus address register needs, and then we are going to assign non-overlapping address range from the system address map, and we are going to also allocate the bus number register. So for bridges, program primary and secondary and subordinate bus numbers registers, so the our bridge is going to know exactly which particular bus range is going to sit behind it. And also we are going to update the command register, and we are also going to update the interrupts and capability setup and all. These are the different functions we are going to have in the phase of my configuration. So our configuration comes into play after enumeration has been completed. So if I want to compare this enumeration and configuration, so the goal of enumeration is to discover what exactly existing and what is the topology of my PCA hierarchy. And the goal of this configuration is to program whatever the discovered devices which was discovered in your enumeration, and it is going to program all those particular devices. And the key action of this enumeration is to probe the vendor ID at each BDF bus device function and recurs through the bridges. Whereas in the case of my configuration, I'm going to update the bar. That means bus number, registers, command bits, and capabilities, everything I'm going to update. And the output of this enumeration is a map of bus, device, and function locations and bus numbers. I'm going to get every information about everything. And in configuration, the output of this configuration is I'm going to update all the devices with valid addresses enabled and ready for the traffic. And timing, coming to timing, in the case of my enumeration, it is going to happen first from top to bottom and the depth first. Whereas in the configuration, it is going to happen after the enumeration is happened, and it is going to have per device. And it is performed, the enumeration is performed by the operating system, and this configuration is also going to happen by the operating system itself. Now, we have studied about this bus numbering and all in the case of my PCI, but in PCIe, we are not going to have any particular physical bridges. But why do we have this bus numbering? So, PCIe has no shared electrical bus. So PCIe has no shared electrical bus. So every PCIe is a dedicated serial point-to-point connection between exactly two ports, right? And there is a no shade wire that many devices are byte for, and the way there was in our parallel PCI. So but PCIe is still talking about buses and their bus numbers. Why? Because the software is still compatible with PCI. So operating system, the BIOS operating and the enumeration software were built around this PCI bus numbers only. So that's the reason still in PCIe also the addressing model is still configured in BDF functionality only. And whatever the bus numbers and all we are going to have, those are not physical bus numbers, but these are logical. So a bus number in PCIe is a logical identifier, and it's not a physical number we are going to have. And we still need unique addressing, which is required for our particular OS to configure and all. That is the reason we are still maintaining this bus numbers. And we are going to have root ports and switches which are going to act as a bridge, but it's not a physical bridge, it's a virtual bridge which we are going to have. Now, what is a root port? We need to understand this particular thing also. What is a root port? So basically, a root port is a PCI port on the root complex and the logical block usually inside the CPU or the chipset. And it is going to connect the processor and memory to the PCI fabric. And its responsibilities are hierarchy origin, where it is going to begin a new bus or device or function in a branch. And it is a transaction translation between internal fabric and PCI TLPs. So what do I mean by TLPs and all? We are going to discuss in our next upcoming sessions. And it is going to have the error handling and contaminant, and it is used for advanced error reporting, and it is going to support plug and play model and link power management and interrupt handling. So you don't need to worry about all this particular new terminologies and all. Anyways, we are going to discuss this everything in our upcoming sessions. This particular session agenda is to understand the basic terminologies, like what do you mean by enumeration, what do you mean by configuration, what is enumeration and what is happening in the configuration, and what is why we are using bus numbering and all, and what is a root complex and all. And we need to also understand about what is a physical and what is a virtual bridge. So basically a physical bridge, we are going to have actual PCI to PCI bridge, whereas in the case of my virtual bridge I'm not going to have a physical bridge. So a root port or a switch, it is going to act as a virtual bridge. Okay. And it is in the case of my physical bridge, it is actually used to connect multiple buses, but in the case of my virtual bridge it is used to preserve the PCI enumeration. Okay. And we are going to have the configuration header as type 1 configuration header in the case of my physical bridge, whereas in the case of my virtual bridge also I'm going to have the configuration as type 1 header. Now what do I mean by this type 1 header, type 0 header, and what is this in the configuration, that we are going to discuss anyways in the packet structure we are going to discuss. Okay. Yes. And this is bridges in PCI versus PCIe. Yes. So the major agenda of this particular session is to bring you a clear idea about the basic terminologies, so that when we are discussing about the packet structure and when we are diving deep into the packet structure and all, and when we are encountering these terms, you will be striking like, I know this particular term and all, so you will be confident about this all terminologies and all. Okay, yes, so that's about this particular session. If you like this video, please like, share and subscribe to my YouTube channel.